It's my pleasure to welcome Nada Lavrač from the Josef Stefan Institute in Ljubljana, Slovenia. Nada, you probably don't remember me. We met a number of years ago in Brussels in 2013 for a reviewing week for the Marie Curie projects, where you were my senior responsible expert. And I was one of the newbie reviewers, completely overwhelmed with all the chaos. I remember how impressed I was, how straight and organized you handled everything. When we discussed among our chairs names for keynote speakers, I learned more about your research and was likewise similarly impressed. So Nada Lavrač is the head of the Department of Knowledge Technologies at the Josef Stefan Institute, which is the leading research institute in Slovenia. She's also full professor of computer science at the University of Nova Gorica, also in Slovenia, and deputy head of information and communication technologies program at the Josef Stefan International Postgraduate School. She was visiting professor in Bristol and Klagenfurt and received a number of awards. For example, she was already elected ECHI Fellow in 2007. I checked her name on Google Scholar this morning and the age index was 54. Her research interests are in knowledge technologies, in particular in machine learning, data and text mining, knowledge management, and computational creativity. Her special interest is in supervised descriptive rule induction, and I think that is the area in which we hear the talk today. Her main application areas include medicine, healthcare, and bioinformatics. So as I said, today she will talk about semantic relational learning, not only about relevant algorithms, but also about the data mining workflow platform Cloudflows that makes those algorithms available for ordinary people like me. So Nada, we are happy that you're with us. Welcome again, and the Zoom floor is yours.
Thank you very much, Francisca, for the kind introduction. I realized that by the time I sent you the little note about my CV, I stopped being head of department after 16 years of duty as head of Department of Knowledge Technologies. I didn't run for another term and my duty stopped in March. Now I'm working as a senior research counselor at the same department. So the talk is about semantic data mining, and the talk will be organized as follows. First, I will present some background on machine learning. After all, this is an artificial intelligence conference, and it is not necessarily that everybody is expert in machine learning. Then I will switch very briefly to relational learning with some focus on my own work. And the difference between machine learning in the relational learning, that the input data to each of the two frameworks is slightly different. In standard machine learning, the input data is in the form of standard tabular data format. However, in relational learning, we assume a relational database as input to a relational learner, or even some other relational structures, which could include graphs and networks. The central part of my talk is about semantic relational learning, where in addition to having relations in the data, we are also taking into account background knowledge in the form of ontologies, or recently in the form of knowledge graphs. And I will present our own approach to semantic relational learning, how you can deal with a situation where you would like to enhance the learning process and improve the learning process by taking into account also the concepts from human encoded ontologies or even from automatically constructed knowledge graphs. Another issue I will address is the use of network analysis for improving semantic relational learning. Namely, you can imagine that if knowledge graphs are huge, or ontologies may be huge, as well as data can be big in terms of big data analytics, the search space for finding appropriate models can be huge. So the issue is, can we transform the data into large networks and by traversing the networks, find just the most important nodes in the network and use those nodes in semantic relational learning to speed up the learning process. Finally, I will try to summarize and present some issues as well as some hints for future work. So just to introduce you, machine learning starts with some data table, and the idea is to find a set of rules, a set of interesting patterns, or a classification model which kind of compresses the data and allows for use in a classification setting. So these models can be either black box models or symbolic understandable models which allow for explanations. So if we look at the table, we see that some rows in the table correspond to training instances or learning instances from which the machine learning or data mining algorithm will learn the model, and the columns correspond to attributes, variables, which have specific values, which can be either symbolic or numeric. Finally, there is usually a classification attribute, which is colored in yellow on this slide. And the goal of machine learning is usually to learn a classification model which will allow for classification of new instances which have not been pre-classified in advance. So for instance, if we are in a medical learning setting, we have data about the patients. We have the class attribute corresponding to a set of possible diagnoses for the patient, and the model will then be constructed from the data and can be used for classifying new patients arriving to the medical doctor. And this model can serve as another expert opinion in classification. So in black box models, we can use them for classifying new instances, but black box models like neural networks don't provide sufficient explanation. However, symbolic models or symbolic patterns do directly provide for explanations. And a case of such simple and very effective and explainable model is the model in the form of a decision tree. So for the particular data set, which corresponds to patients who came to an optician to get contact lenses, this decision tree says that, well, if tear production is reduced, the patient didn't get contact lenses. However, if tear production was normal, which means that the person produces enough tears or his eyes are not sore, then the decision depends on astigmatism. If the person has astigmatism in the past data, nobody got lenses, which would be hard. Only soft lenses were assigned. However, if the person has astigmatism, it depended on spectacle prescription. Either person got hard lenses if the person was myopic, otherwise, in case of hypermetropic, no lenses were assigned. So an alternative to symbolic model construction for classification purposes is learning of symbolic rules. Here we again see that a rule can be read from the right to the left. If tear production is reduced, no lenses are assigned, or alternatively, if tear production is normal, if a person has astigmatism and spectacle prescription is hypermetropic, the person is not assigned any contact lenses, and so on and so forth. And finally, at the end, a set of rules. If none of the rules fires for a new instance to be classified, a default rule is assigned, which corresponds to the majority class. First generation machine learning algorithms started being developed in early 70s and also early 80s. The famous names being Ross Quinlan, Richard Michalski, Leo Breiman, and interestingly, Ross Quinlan, who was a machine learning person, and Leo Breiman, who was a statistician, parallelly developed decision tree learners without knowing of each other. So these first generation machine learning algorithms were characterized by learning from data stored in a single data table, relatively small sets of instances and attributes, which means small sets of rows, small sets of columns in data tables. However, a lot of new research started to emerge in the 80s with the emergence of new machine learning conferences like International Conference on Machine Learning, European Machine Learning Conference, and special sessions at ICHKAI, ECHAI, AAAI, and so on. And researchers started addressing new learning tasks and started developing new algorithms. One of the important issues was that in early 90s, researchers who were involved in the project called CRISP started developing the entire data analysis pipeline, which proved to be very important for kind of structuring the machine learning process. Namely, machine learning is just one of the steps in the entire process of knowledge discovery in databases. So here, I don't know if you can see my mouse. I'm pointing at the step which refers to machine learning and data mining, referring to applying a machine learning algorithm or a data mining algorithm on the tabular data, which we have obtained from the data which we have available, for example, in a large data warehouse. However, the entire process doesn't consist only of data mining or machine learning. The process consists first of selecting the appropriate data for analysis, finding the interesting parts of the data in the available data store, then manual data pre-processing, where the data is transformed into a tabular format, here the blue part here, but there can be some data in other data formats, including texts, including graphs, and including relational databases. And then there is a so-called automated transformation step, which transforms this potentially heterogeneous set of data, including data tables, but also some other background knowledge, into an appropriate tabular form, which is appropriate for standard machine learning. Using machine learning, you can then induce classification models or find interesting patterns in the data. And finally, there is, of course, an evaluation step before you can say that something you have automatically constructed from the data really represents human knowledge, which is useful for the humanity. Of course, in this second generation machine learning, time of second generation machine learning resulted in interesting new algorithms for learning predictive models, for learning classifiers, including Bayesian network learning, support vector machines, but also relational learning started to be developed in early 1990s with the work of Ross Quinlan on the FOIL algorithm and with the work of many of my colleagues who were involved in the community called inductive logic programming and relational learning, where we addressed the problem of learning from multi-relational data and learning symbolic models out of that, typically in the form of prologue clauses. So the first inductive logic programming workshop was organized in 1991, and I was happy to attend this workshop, which was extremely stimulating and nice. On the other hand, a lot of work in data mining started to appear, and as opposed to machine learning, which is usually focused on learning from pre-classified data in order to build classification and predictive modeling, predictive models, data mining is usually concerned with finding descriptive patterns in the data, finding some interesting rules in the data, symbolic rules, which explain a part of the population and not necessarily a model which models the entire data set. So can we focus on some particular subparts of the data and explain the groups of the data which have some, according to some similarity measure or according to some other measure. So in this way, in data mining, association rule learning framework was discovered, as well as subgroup discovery, which was one of my focus of interest in past research. So subgroup discovery is characterized by having data in tabular form. Here our classification variable is in the form of, it has a binary form, yes or no, or 1 or 0. And what we are trying to find is the explanation or interesting symbolic rules which explain the positive class. So for instance, here we would be interested to find out rules explaining who got contact lenses. And this positive class is usually called the target class, the positive target class. So in subgroup discovery, a task is to find individual rules or individual interpretable patterns in the form of rules which are induced from the data, labeled by this predefined property of interest. Subgroup discovery algorithms then learn several independent rules that describe groups of target class examples. So this is illustrated here. So it is not necessarily that we build a model which would be able to classify instances for class A, distinguishing the instances from class B, but we find independent rules which explain parts of the data of the positive class. So several machine learning algorithms were developed for subgroup discovery. A number of applications in specifically medical applications were developed. For instance, just to give you an idea of a medical application, we would have, let's say, patient records described by an amnestic laboratory in ECG attributes, and we would be trying to find and characterize population subgroups with high risk for coronary heart disease. And these groups should be large enough, which would mean that they cover significantly large number of the population, but also distributionally unusual in the sense that these rules should cover a lot of positive examples, namely examples of high-risk coronary heart disease patients, as opposed to covering also possibly some very small amount of negative instances. So for instance, the first rule would be that a person has high risk of coronary heart disease if the person is male with positive family history and age over a certain age limit, or a female with large body mass index and age over 63 years. So several rules of this kind would explain subparts of the population and would characterize it. And these rules, since they are symbolic, can be used also for patient screening purposes. We developed also additional components of such subgroup discovery algorithms, namely additional explanation through finding supporting characteristics computed using chi-square statistical significance test, which would say that for the group of female patients, additional characteristics which explain this subgroup would be positive family history, hypertension, increased LDL cholesterol values, and decreased HDL cholesterol values. So also we used it in functional genomics settings where the data is characterized by a relatively low number of instances, but huge number of attributes or variables. In particular, several thousands of genes would act as variables in such a large data set. And the task would be to find interesting subgroups describing patterns, describing like for cancer type leukemia, trying to find which genes are differentially expressed and which genes are not differentially expressed for a set of patients with leukemia. These algorithms were developed within the Orange Data Mining Toolkit. It is a data mining platform developed at the University of Ljubljana, which involved a large number of algorithms. What was also interesting at that time is that Orange was one of the first data mining platforms which allowed for data mining workflow construction. So you can see here at the right-hand side a workflow which takes a file with a data file which discretizes the variable and then builds subgroups by a subgroup discovery algorithm, in particular one of the ones which we have developed in Ljubljana, like SD, standing for subgroup discovery, a priori SD or CN2 SD algorithm, which were all made available within the Orange platform. Then we could visualize the data and provide a projection of the data, as well as a kind of statistical analysis of the subgroups. The nice thing about contemporary second-generation data mining platforms that they allow for many data mining algorithms, allow for data and model visualization, but also enable complex workflow construction, including data and model visualization. And the nice thing is that you can build such workflows from pieces of code which are made publicly available. So the problem of these platforms was that they didn't include algorithms for mining complex structured data and for efficient relational data mining, which remained a great challenge at the time. Another issue to be emphasized in the second generation data mining algorithms was that although the KDD process already addressed the issue of manual data pre-processing and automated data transformation, automated data transformation was never considered as an important step of machine learning. However, the process itself already assumed such an automated data transformation step. Nowadays, there is a huge popularity on so-called representation learning, which actually does refer to this automated data transformation step in the entire KDD process, which was identified already in the 90s. So transformation requires handling not only the data in the data table, but handling the heterogeneous data available in the so-called background knowledge available to the learner. So these data can be feature vectors, documents, pictures, data streams, and the background knowledge can be multi-relational data tables, networks, text, and so on. So how shall we design such transformations to handle such data? So you will see that in the relational learning approach, my own work corresponded actually to representation learning step in relational learning. So what is relational learning? It deals with learning from multi-relational tables, so single data tables which are interconnected through foreign keys. Again, we are interested in finding models for classification or finding interesting patterns in the data. So the terms relational learning, relational data mining, or inductive logic programming all denote learning from complex multi-relational data, from complex structured data, like in this case, let's say molecules. We have molecules which are described with some attributes, but then molecules consist of several atoms. So we have one-to-many relationship here. We have properties of these atoms, and then atoms consist of bonds, which have also some properties. So we would like to, for instance, find a rule which will distinguish mutagenic molecules versus non-mutagenic molecules, but involve such a complex structure in finding the properties of mutagenic molecules. So in our own work, to deal with this situation, we developed transformation approach called propositionalization, which was an approach to data transformation into symbolic feature vectors. Nowadays, there are other approaches referred to as embeddings, which refer to data transformation into numeric feature vectors. So propositionalization is transformation into symbolic feature vectors of value 0 and 1. On the other hand, embeddings typically involve data transformation into numeric feature vectors. Embeddings are out of the scope of this talk. However, the big difference is that propositionalization refers to kind of sparse symbolic feature vectors, whereas embeddings refer to condensed numeric feature vectors obtained typically through weights of neural networks. So propositionalization was developed as means to transform multi-relational data into single data representation format with features, complex features representing the attributes and feature values, zeros and ones, representing the values of the truth values of these features. So in the first step, the first step referred to constructing the relational features and the propositional table out of these relational features. And then the second step was using whatever machine learning or data mining algorithm on top of such simple tabular representation. Possibly also not only learning models, but also finding interesting patterns through subgroup discovery. We developed a number of relational subgroup discovery algorithms and relational machine learning algorithms, one of them being relational subgroup discovery, RSD. And to illustrate its performance on this complex data structure of mutagenic molecules, some complex features were automatically constructed, like a molecule has an atom which is of a certain type, or a molecule has a property luma which should be less than a certain luma threshold. Then the transformation into tabular data format was performed by binary feature value construction, and then a standard subgroup discovery algorithm would be used on top of such tabular representation, finally getting a relational rule of the form. So a molecule is mutagenic if feature 121 is true, which means if the molecule has an atom of a certain type, and if this feature is true, if the value of luma is less than a certain threshold. So all of this was developed in the form of workflows within the ARM for web services data mining platform. Other prepositional algorithms were developed, RSD by myself and my colleagues, 1BC by other colleagues, RELF in Bristol, RELF by colleagues in Prague. Aleph, ILP Learner, was the most famous and still useful. And Aleph, which is an inductive logic programming algorithm, has a particular functionality which is called featureize, which refers to propositionalizing a multi-relational data set. Another approach was developed by our group called wordification, which transformed relational data into kind of bag of words format applicable to text analysis. In this wordification approach, a multi-relational table is transformed into feature vectors for each of the tables separately, and then these feature vectors are concatenated into a simple tabular representation, which can be used as kind of word representation, and then you can use machine learning or text analysis algorithm on top of that. And I will not go into the representation itself. Just to mention that large speedups were achieved through wordification. improved accuracy was achieved with this algorithm compared to other propositionalization algorithms, and recent advances were presented by our colleagues from Brazil at the recent conference on inductive logic programming in 2019. Let me now switch to semantic relational learning, where the idea is that we don't have only the data available, either single table representation of the data or multi-relational data, but also domain ontologies or knowledge graphs as background, which is to be used in the learning process. Again, the task is to build models, classification models, or find interesting patterns in the data. And to do so, our data has, and the ontology concepts have to be kind of, there should be some mapping or annotations where the variables from the data set are kind of annotated to the concepts of the ontologies. So let's look at this particular ontology called the gene ontology, which consists of many genes which are described in terms of their functions, processes, and components. And there is also a hierarchical structure, is a and part of relations between these concepts in the gene ontologies, and the levels of the ontology represent term generality. So we can have some genes at the bottom level of the ontology and gene groups at the higher levels of the ontology. So this would be the particular background knowledge which can be applied to DNA microarray data analysis. And what we do in our propositionalization approach to semantic machine learning is that we construct complex features again, which would correspond to some concepts in the gene ontology. So ontology terms were in our approach represented as logical facts in prologue. So for instance, for a certain gene with a particular gene number, its component would correspond to a gene ontology term named so much and so on. And then we can interactions of genes, which are, let's say, gene 2534 interacts with gene 4803. And then we can, in propositionalization approach, in the algorithm called RSD, relational subgroup discovery, we automatically construct complex features, like feature enumerated with number 2, refers to genes, and A is a variable denoting a gene, which corresponds to this particular component in the gene ontology. But we can have also more complex features which are automatically constructed, like gene A interacts with gene B. The function of gene B corresponds to a particular gene ontology term, and it also corresponds to the term denoting the component. Then through propositionalization, we determine truth values of features and then learn rules by a certain subgroup discovery algorithm like CN2SD. So this first order feature construction is the most important part of the propositionalization algorithm. And these complex features are automatically constructed. Note that in some logical features, we can have variables like variable v, which doesn't appear in the head of the clause. And there are conjunctions between these constituent sub-features. We would construct such features with a certain threshold on support, where the support should be above minimal support. Now we have these complex features. We put them into columns as variable names. We put positive examples here, differentially expressed genes. We have negative examples here, random genes which are not differentially expressed. Now we have a tabular representations of zeros and ones, one representing that the feature is true for the example feature 2 is not true for the example, and so on and so forth. So we have now a binary representation of the complex data, including ontologies. And now we can learn rules from such data. For instance, a gene is, if we try to find rules for the positive gene group, a gene is differentially expressed if feature 2 is true and feature 3 is true, and such a representation, such a rule covers 4 out of 5 positive examples. Number of other propositionalization approaches were developed in our group, including an adaptation of the Aleph inductive logic programming algorithm, which we called SDM-Aleph, SDM standing for semantic data mining. A particular algorithm, Hedwig, was developed by one of my PhD students. Then we developed an approach to mining heterogeneous networks by another PhD student and by 2 other PhD students. And finally, we developed also an algorithm which allows us to speed up semantic data mining through network analysis. So in heterogeneous graph analysis, it's a similar idea of propositionalization, where we can have texts, we can have networks, we can have properties within the networks, and we construct feature vectors of each of these representation for each type of the representation, but then we concatenate the vectors into feature vector format, tabular feature vector format. However, here we don't have binary features, but we have weighted features obtained from personalized page rank transformation and walking through the networks. Finally, I address some advances in network analysis for semantic relational learning, where the challenge is that if we have semantic web on the one hand, through which we are able to find complex rules which are highly informative by means of semantic data mining. However, they are extremely, the computation is very demanding in terms of computational complexity, and the complexity grows exponentially with the size of the ontologies. On the other hand, in data science, we can process massive data fast and easily. However, we get typically much less informative results through network analysis, which is frequently used in data science. Now the question is, can we combine the 2 approaches and get fast, scalable, and informative rule learning approaches in semantic data mining? So the idea of trying to reduce the complexity of the huge search space of ontology terms by network analysis was addressed by a PhD of Jan Krall and was published in JMLR 2019. In this approach, we use network analysis, particular personalized page rank, to estimate the importance of features, ontology terms in the huge knowledge graph. And by means of searching for important feature, we can use the complexity, which can reduce the complexity of this huge search space. We achieved about 100% speed up through an approach which is illustrated in this picture. We have the data, we map it through annotations and mapping to the network nodes of the ontology. We use personalized PageRank to walk around this ontological structure. We discard low-ranking nodes and then use only these low-ranking nodes for semantic data mining and for explaining the positive data against the negative examples. So this is further illustrated. We have a 3-step approach: estimate ontology term relevance, delete terms with low relevance, and run semantic relational learning algorithm Hedwig on the pruned ontology. So these steps are illustrated here as well, and illustrated also on a practical example from the analysis of acute leukemia, where we have data about gene expression of data of patients with acute lymphoblastic leukemia. We have the background knowledge, particularly here the gene ontology. We have positive examples noted in green. We have the negative examples noted in red. When running with personalized PageRank in the ontology structure, also taking into account the hierarchy, the relationship between the concepts in the ontology, we can reduce the entire set of all the concepts in the ontology only to the relevant parts. For instance, the relevant nodes remaining only cell surface receptor, signaling pathway, binding, plasma brain, and immune system process, which can be used by a subgroup discovery algorithm to explain the positive data. As mentioned, personalized PageRank proved to be effective to decrease the size of the search space of semantic relational learning algorithms. Accuracy of the final model didn't decrease, even by significantly decreasing the size of the background knowledge to less than 5% of the entire search space. However, finally, the time taken to discover rules on pruned background knowledge was shortened by a factor of 100, which proved the efficiency of the proposed approach. In conclusion, our propositionalization approaches, let me emphasize that in nowadays terminology, these propositionalization approaches could be interpreted as embeddings, as automated data transformation approaches. The difference being that our approaches to propositionalization are typically resulting in sparse symbolic matrices, whereas nowadays embedding approaches result in dense tabular representations. Note, however, that prepositionalization can also be applied as a pre-processing step to embedding, to getting dense vector representations. So the two things can be combined, and actually we have combined the two approaches in our recent work. So our propositionalization approaches can allow for structured data flattening as a data pre-processing step to modern data mining, including deep learning. It can be applied also to heterogeneous information network mining, as shown by our colleague Gerchar. It can be also used to multi-relational setting through wordification, and all these implementations were publicly available through Cloudflow's third generation cloud-based data mining platform. To wrap up, nowadays there is a lot of available knowledge on the web, including large ontologies and including large knowledge graphs. Mining of knowledge graphs is an issue which is recently addressed also through graph embeddings, network embeddings, and so on and so forth. But they can be addressed also through the propositionalization approaches which I have outlined in today's talk. Results of our group shows that promising results can be obtained for mining both linked open data, knowledge graphs, ontologies, and current work of PhD student Blaž Krl proves that knowledge graphs can be effectively mined. In summary, what I have shown was a brief introduction to machine learning, to relational subgroup discovery on the one hand, but also using semantic web and particularly ontologies available in the semantic web as background knowledge available to machine learning algorithms, which resulted in so-called semantic relational learning or semantic subgroup discovery algorithms, which I have briefly outlined in my talk. In this way, I would like to conclude my talk, and I'm ready for questions.
Okay, so thank you again, Nada. And well,
and thank
we
you
see each other in the coffee room.
for the
Yeah.
invitation and the opportunity. Goodbye.